In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 4, Constitutive Relations, Part 7. Continuing from the previous part, we are going to talk about the loading history. What do we mean by loading history? If we have the three-dimensional strain space like that, the plastic strain space, epsilon 1p, epsilon 2p, epsilon 3p, like the stress space, then this is the path for plastic strain, okay, going from 0 to point Q. Now we could reach point Q by different strain paths. For instance, we could go straight to point Q, but we could also go through a point like that, which we call it a strain path. We are going to talk about this phenomena. Right. Now, each material particle undergoes a plastic strain history, such as the path shown in here. So, plastic strain history, what we mean by that? We mean that the loading that the material has gone under before reaching a strain point. So it could have different histories like that, or other histories as well. Okay, at point Q, the plastic strain is epsilon IPQ. The effective plastic strain at Q must be evaluated through an integration over the complete history of the deformation. So if we put here epsilon bar P Q, what do we mean by that? Because it has three components, epsilon 1P, 2P, and 3P. These are the principal strains. So we have to write this equation to get the incremental strain and then do the integration from 0 to Q to get the total strain. Now, which path do we go through? This one or that one? That's important. So if we put this and integrate this, we can get the strain. Note that the effective plastic strain at Q, this is very important. Note that the effective plastic strain at Q is not simply epsilon IPQ. In other words, it's not simply by putting, if you just put this value into these relationships like that, you don't get the total plastic strain or the effective strain. Hence, the definition of an effective plastic strain increment is given by this. This is the effective plastic strain. What do we mean by this? If you put Q here, you don't get the effective plastic strain. I will explain this in a minute. Let me just give you an example to illustrate this point further. Now take this metal bar. Okay, this metal bar has a 100 millimeter length. The thickness of this bar is 10 millimeter, and the width of the bar is 10 millimeter. And we are applying a force F. Okay, so next, this specimen goes under deformation in a simple uniaxial loading in two stages. Okay, the first stage is this one. We are applying load F, and it elongates, so the length increases from 100 millimeter to 110 millimeter. Obviously, the thickness and width change because the volume is constant. If the length is increased, this must decrease. Now, in the second stage also, we reverse the loading. Okay, we reverse the loading and apply a compressive force and reduce the length to 105 millimeter. Okay, so note that here we have applied a uniaxial tensile load, increased it to 110 millimeter, and applied a uniaxial compressive load and decreased it to 105 millimeter. Supposing no buckling or any other distortion happens, okay, just a uniaxial tensile elongation and uniaxial compressive compression. Okay, that's what happens. That's what we assume. No other distortion happens. Okay, only uniaxial deformation happens. With this assumption, we are going to see what strain the bar has experienced. Okay, what is the strain? The final strain. What is it? Okay, so to answer this question, we say that it is correct that this has gone through a middle stage to reach to the final stage. But the original length is 100 millimeter, the final length is 105 millimeter. So the final strain is 0.049. Is that correct? Let us do it another way. Calculate the strain another way. Stage by stage, from this stage to that stage, and from that stage to that stage. If we do that, stage 1, this one, from 100 millimeter to 110 millimeter, we get 0.095 for a strain in a stage 1. And for a stage 2, 110 millimeter to 105 millimeter. So we get 105 to 110, and I have written it in this notation because I don't want to get these minus signs, because just minus signs just says that it is compressive. I just want the magnitude. So for the stage 2 also I get 0.047 the strain. So the total strain from here to here, so if we add up this together, I get 0.142 is the total strain, which is the summation of strain of stage 1 and stage 2. So you can see it's very much different from this one. Here we calculated the final strain as 0.049, and here we have calculated it as 0.142. So why so much difference? If you look at this number and that number, you will see that there is a lot of difference, almost 3 times, almost 200% different from this to this. Okay, why is that? Because in the first one we did not consider the strain history, loading history. We just considered the initial and final stage. Okay, that's what happens in real physical forming problems, metal forming problems, for instance, when you form a sheet of metal, or when you forge a component, anything, when you form them, change the shape of the metal, then you get this kind of strain. In fact, there are some strain loading histories which cause intermediate strains which we do not see. So if we just take the initial and final stages, we don't get the right answer. As you can see, this is the right answer. 0.142, 0.049 is not correct. Okay, so that's the difference between this and that. And the statement that I made earlier in that slide and said that if you put the Q in that equation, you won't get the right answer. It's because of this. Okay, so now you understand what loading history and a strain path means. For instance, I could go to here like that. I could go through here. So different paths to point Q can be made. It depends on the actual operation that we do on the metal. Okay, so what operation are we doing? Are we using rolling operation, forging operation, extrusion, any operation that we do form and change the shape of the metal, that gives us different strengths. Obviously, these kind of analysis are done in metal forming analysis, which is another course. Okay, so we understand what strain pass is, and just I mentioned here that this example that I illustrated is a very simple example. It's a uniaxial loading, okay? But here we have multi-axial loading. So this figure is not for this example. It's just I just illustrated a simple example to get the concept, okay? The concept is the same, but obviously for multi-axial loading we don't have this kind of equations and more complicated. Okay, let's see the Prandtl-Ross equations in terms of effective parameters. Remember, this was the Prandtl-Ross equation we introduced earlier on, and this is the Levy-Mises equation, and this is the effective parameters. We mean this. Sigma bar is the effective stress, d epsilon bar p is the plastic strain or effective plastic incremental strain. We could now express the plastic multiplier, this d lambda, because this is a relationship between deviatoric stress and incremental plastic strain. From these equations, we could get d lambda equal to 3/2 d epsilon bar p sigma bar p, okay? And so we obtain this plastic multiplier. And using these equations that we had before, remember we had these equations before, and the plastic multiplier that I have just obtained, we could have these equations in terms of just substitute this for the lambda, and we get these equations like that. Also, the shear incremental plastic strains, and all of these could be simplified into this tensor notation: d epsilon ijp equal to 3/2 d epsilon bar p sigma bar sij. Okay, so what we meant here by Prandtl-Ross equations in terms of effective parameters is this equation. Now let's do an example. Here is an application: combined tension torsion of thin wall tube with isotropic hardening. Of course, we considered this problem of combined tension torsion of a thin wall tube for the yield criteria. But here we are going to take this a step further with isotropic hardening. Okay? So, the von Mises yield function in terms of the axial stress and shear stress, we obtained it before. It's like this: F0 sigma ij sigma squared 3 tau squared under the square root minus 1 minus y is equal to 0. Now this is the yield criteria for Tresca and Mises. Here we are going to take the Mises. The yield is like this. If tau is 0 and we increase sigma, which is that force there, the stress there, if it reaches y, it yields. But if y is 0, we don't apply any axial force and apply only torsional force, then the shear stress reaches y over root 3, yielding occurs. Okay, now we are going to step further for isotropic hardening. This defines the ellipse, as I said, and now the subsequent yielding, this is the, we put 0 here, it means initial yielding. It means this point, the points on the ellipse, okay? They are F0. Now F is a bit further. If we go some points here, okay, isotropic hardening. So F sigma ij k ij, okay? So this equation becomes this. It means that we have gone a step further, so we could put F0 sigma ij minus k. Instead of F0 sigma ij minus k, I can write sigma bar, that's the effective stress, minus y plus k. Why did I write this? Because I have put instead of this sigma bar, because this is the effective stress. These are the stresses F and tau acting. These are the forces, loads F and T. The torsion are the loads on the thin cylinder, and they cause the stresses sigma and tau, and that's what we obtained before. In fact, this relationship is sigma bar, so we could write sigma bar minus y minus k. This y is capital, this is small, it doesn't matter, we can write all of them capital Y. Therefore we can write the function for the isotropic hardening as this, okay, and we could write this as F0 sigma ij minus k, so it's sigma bar minus y plus k is equal to 0. That is the flow equation. That's the constitutive relation, okay? Whereas the initial yield surface is the ellipse, and with major and minor axis y and y over root 3, subsequent yield ellipse has the axis y plus k and y plus k over root 3. This is the initial yield, okay? This is what we had here. We had here, that's the initial yield, or F0, that's F0. And as we go further along, I mean, increase the torsional loading and the axial loading, we go further away from these. So that's the state of stress at point K. So y plus k root 3 instead of y, that's k, okay? That's k here. So that is our yield surface, which is advancing, okay? Because if we take the strain hardening effect, then if we unload this thin cylinder and then load it, the initial yield surface now is this, not that. In fact, it doesn't yield if I load it to a point like that. I have to reach here in order to yield the material, because the material has gone under a strain hardening effect, okay? It has become harder due to straining and working. So that's why we have drawn this yield surface like that. So if we go further, it goes further, and we may reach a point that fracture happens. Now, Prandtl-Ross equation in terms of effective stress and effective plastic strain reduced to these equations. Okay, the previous equation reduced to these equations for this problem. Okay, I have put the other components equal to 0 like before, because we solved these Prandtl-Ross equations for this problem before. I'm using those instead of d lambda. I have substituted the equivalent of d lambda or plastic multiplier. Now, we consider again, if you remember the way we loaded in here, I just repeat it. Consider the case where the material is brought to first yield through tension only. So the first loading that we are applying on this thin cylinder is not torsion plus axial load. In fact, we don't have any torsions. We just have axial load. So we increase the axial load until we reach the yield. Okay, so according to von Mises condition, sigma equal to y is a uniaxial loading is equal to y. So that's the first yield. Now, after the first yield, it says, like before, let the material then be subjected to a twist or torsion while maintaining the axial stress constant. Okay, we keep this axial stress as sigma equal to y and start increasing this torque or twist or torsion. The expansion of the yield surface is then as shown. Okay, you can see here, this is the plastic loading. This is the initial yield. What we have done in this problem is this. We have this yield surface for the material. Now, according to Mises, we have started loading in that direction. We haven't put any loading in that direction, just in the axial sigma direction. Okay, so we have increased the loading until we reached y, which it has yielded, and then we have stopped increasing y. So we have stopped at this value, sigma equal to y, and started to increase tau. Okay, so if we stop here, unload it, then we get this. This is the shape that we get for our material. And then again, if we start loading, depending on which way we are loading, we have to reach this curve in order to yield the material. So you can see how this isotropic hardening works here. And introducing the plastic modulus. In fact, plastic modulus, you remember, was the gradient of the curve. Okay, that h was h. It was d sigma bar to d epsilon bar p. Okay, this was the curve for effective stress, effective strain, and this is the gradient of the curve. Obviously, at each point the gradient is different, so depending on where we want to obtain the plastic strain, which point is our objective. At that point we obtain this h, and we substitute in the relationship. So that's why we put 1/h here, and we get this relationship. Okay, this is for where we have gone into the plastic. Here is the initial yield. Here is after we have gone into the plastic region. So we get this relationship, and then using this relationship and using sigma bar equal to y squared plus 3 tau squared. Remember, this is where we started our plastic deformation. In fact, instead of sigma we put y. We are on the initial yield, and then after that, whatever loading is increased, we go into the plastic region. So this is the effective plastic stress. Okay, effective plastic stress. So if we use this and this relationship, we get the plastic strains. You see, here we get the plastic strains, and this h is the gradient at the point where we get this plastic strain. So these are the values for the incremental plastic strains. Now we could integrate these and get the plastic strains. Okay, that's the initial yield, and that's the plastic. Now here I have used the linear hardening. Of course, we could use a non-linear hardening, but linear hardening is easier. So I can integrate it like this. Using this relationship, I can integrate these three equations to get the plastic strains. Okay, so that's what I've done here. Integrating, I have integrated this equation using the previous relationship, and therefore I get the strains: epsilon xx, yy, zz, and xy. These are, of course, I have the shear strain due to the torsional loading. If I just had the axial loading, I wouldn't have a torsional strain or shear strain. These are the stresses and strains. Stresses, normal and shear, so we have the normal and shear strains as well, and these are the values. Okay, these are very useful. In fact, if you load this cylinder by pressurizing or axial load or torsional load, you can get how much deformation, plastic deformation you get in the cylinder. It could be used in the design problems, and of course this is a simple application. We could have more complicated applications in here. The results are presented in here for case of mu equal to 0.3. This is generally for metals, EH over 10 also. And the axial strain grows logarithmically and is eventually dominated by the faster growing shear strain. We can see here. Okay, so this is epsilon xx. Of course, we could draw epsilon yy and zz, but here we have drawn epsilon xx and epsilon xy. As you can see, as we increase this tau over, when tau of course is 0, this is 0, but epsilon xx is not 0. Epsilon xx is something here, okay, equal to that. But as we apply this torsional loading, we get this epsilon xy dominating this epsilon xx. Of course, both of them increasing, but the increase is more because we have stopped this sigma xx. This xx is just due to the shearing. So that's how we get the relationship between the plastic strains.